This is a continuation, again, of the last idea. If you recall from yesterday, or from 2 days ago. No, you guys, it was yesterday or 2 days ago? Yes. It was yesterday, yeah. The other class was 2 days ago. From yesterday, we spoke about the concept of refraction. What was refraction in a simple statement?
It's like when light bounces off in a weird...
Yeah, when light
goes through something.
Good, yeah. Like, not necessarily bounces off, but goes through and bends. So refraction is the bending of an EM wave, or the bending of light. The bending of visible light is usually what we are focused on, because as humans, what part of the EM spectrum do we know? The visible spectrum. It's all we really can see. So we don't really care too much unless we're engineers and applying it for something else, but for everyday life and purposes like using your glasses and fiber optic signals from your cable line, we're going to talk about all these ideas and how they're applied. But specifically, the idea behind this whole thing was refraction. Today, what we're going to do is we're going to go to the idea of refraction and think about how can we apply refraction to everyday life, and at the same time, can we do a little bit of math with that? The beginning of this lesson is a pretty straightforward part. As I get toward the middle, in the past, students have struggled with the theory here. So you need to make sure you're 100% focused in and not, oh, you know what, I'm doing something else on my iPad and I'll watch the video later. Okay, because in class, you know that I talk a lot more about how to explain things better and more applications than the videos I record. The videos that I record are really quick and straightforward, so I don't go into a lot of detail about this. So I really highly recommend that you do focus as always. Let's first start with this idea. And this first idea itself is totally what's the word? It's intuitive. It's not counterintuitive like other things have been. So if you think about this is a light ray traveling. It's traveling from the air. Let's say this is the air. And then it hits a pane of glass. So this is like the window barriers. And then the light ray enters through the window. So this is like what you're seeing around you. When the sun's rays hit this window, they pass through glass, and it comes through on the other side back to air. Now some windows are double paned for insulation, for thermal insulation. We'll talk about that later in the year when we get to heat transfer and thermodynamics. Guys, you really need to focus. Whatever you're giggling about or typing away about and laughing about, you really do. So this portion right here is literally a different material, and then it's the same material on the outside. So what's happening is this. The light ray travels, and it wants to follow the path that it's on. It wants to continue on this path. Well, the normal, in this case, the normal is right here. There's our normal. And the normal, if you recall, is the perpendicular line to the surface, just like normal force. So the normal is drawn there. And what happens, instead of this light ray continuing, from yesterday we know, when it goes to a slow material like glass, it has to slow down, so it bends toward the normal. So this is the ray as a result, instead of following the dashed line. Now, that's all good. And yesterday, all we did was talk about one medium to another medium. We didn't talk about a third medium below it. Well, if I go back to air from glass, when I went from air to glass, it slowed down. So when I go from glass to air, what's going to happen then? Yeah, it'll speed up. It'll be the converse or the opposite of that. So as a result, we'll see that this wave, when it comes through here, would want to continue that way. That's a hard one to draw, when you want to use a different color. The ray, when it exits the glass, would continue along the dashed red line with the arrow on the tip of it. But instead, because of the fact that it's now in air, it speeds up. The wave fronts literally go faster. And as a result, when things go faster in the new medium, they bend away from the normal. God bless you. So we've got this scenario here where first you go from air, it hits glass right here, and instead of continuing, it bends toward the normal. Then you go from glass back to air, and instead of continuing, it bends away from the normal. So as a result, what happens here is that the bending kind of cancels each other out. The light ray that actually ends up coming through is this solid black ray right here. That's what ends up getting transmitted. And it's pretty much parallel, or perfectly parallel really, to the original light ray that was coming through. It's just been shifted. You learn in your math course about translations, transformations in general, but a translation is a horizontal shift or a vertical shift. This is literally exactly that right here. This light ray, instead of continuing on this path, continues on a path parallel to it, but just shifted down. It's literally just shifted down. Okay, again, it would continue on this path if it was in air the whole time, but glass causes it to bend toward the normal, air causes it to bend back away from the normal, and it ends up on a path that turns out to be the same exact angle as the path it started at. Just shifted down a little bit. Which one? This one here? Yeah. That's the path that the light ray would take if it went from glass and it stayed in glass. But because it goes into air where it travels faster, it bends this way away from the normal. So what you can recognize here is that the normal, I'm using this phrase normal again, is the line with respect to the surface. Well, here's a second normal in this problem. Because how many interactions are there? Well, first it goes from air to glass, then from glass back to air. So that means that this light ray hits a boundary twice. Once it hits a boundary here, entering the glass, and then when exiting the glass, it hits another boundary. So there's really two normals in this case. The first normal is this red one. The second normal is this blue line. So again, instead of this being the path it takes, because it enters air, it moves away from the normal. This is the normal right here. It moves away from the normal. What's interesting to recognize is the following. This angle right here is the same as this angle right here. I really shouldn't call them both theta I. I'm just going to call the second one theta. Actually, you can call them theta 1 and theta 2, make it easier. Theta 1, just for the sake of this one application. And that's theta 2. So it turns out that theta 1 and theta 2 are the same. And that makes sense because, again, it hits the glass, it bends toward the normal. It hits the air, it bends away from the normal. So inherently, it really hasn't bent at all. It really hasn't bent. It bends while it's in the glass, but afterward, it looks the same. There is an image from the last set of notes that you recall the person's finger was in front of like a magnifying lens on the side, and you saw how the finger looked like it was almost like chopped. It was segmented. Well, while it was in the glass, the light bent, didn't it? But then afterward, the finger was lined up. That's what you're seeing here, really. You're seeing how when that finger was behind that pane of glass, it got shifted over in the glass. But afterward, it came out at the same exact location. So this line is parallel to this line right here. Martha?
So for the two red dotted lines, and then the arrows that are like...
So this is a normal. This is a vector, though. This is a red.
The arrows with the thetas, are those the same?
So this right here and this right here?
Yeah, those are the same, but then are the other two the red and the other?
No, that's so the other red that's here, this red right here is just showing the trajectory it would take if it didn't enter a new material. But because it enters a new material that's allowing it to move faster, it's going to bend away from the normal and end up over here instead of toward the normal. So this is just the dashed line showing the trajectory it would take. That's all. But the angle is from here all the way to here. That's theta 2, and that's theta 1. And those happen to be the same. Okay? Other questions on this? The first intro idea is I want you to see that when you start in one material, enter another, it bends. But if you go back into the same material, it bends back to where it was. Okay? It's like a balance in a sense. You gain 5 and then you lose 5. You're back to where you started. It's like displacement. You walk all the way across the room, you come all the way back. Your displacement is really 0 because the positive distance and the positive displacement and the negative displacement cancel. Angie. Okay. Well, if the third material is not something that was the same as the first, you're saying. So if the third material is like water. So you go from air to glass to water. The answer to that is it depends on what the third material is. If the third material is water, let me think to my numbers real quick. Glass is 1.5, water is 1.3. It will still bend away from the normal because water is actually a faster moving medium than glass. So it would go from air, which moves really fast, glass slows down, But then when it gets to water, it actually speeds up because it moves faster in water. So it would bend away, but not the same as what you're seeing here. So see this red dashed line here? It might bend like away from the normal a little bit, and then maybe the ray would really look like something like that. But if it's the exact same material, air and air, then it will always be parallel to what you started with. Okay? But the third material, it depends on what it is. If it makes it move faster, it'll bend away. If it makes it move slower, it'll bend toward. Okay? Let's take a quick look at this concept of a lens. And why do we talk about lens here, or a lens here? Is because lenses refract light. That's what they're doing. How many, raise your hand, how many of you either wear contacts or glasses? You don't have to be wearing them now. I'm just asking in general. All right, so like 5 or 6, not bad. The class was like 13 and 16. If you ever wear lenses, whether they're contacts or glasses, you know the lenses are making things focus more, right? They're helping you focus on a certain location or focus on what you're looking at. Well, that's not the reason. The reason it's called focus is not arbitrary. It has to do with where the light focuses on the back of your eye. So we're going to talk about lenses first, then we'll talk about corrective eyewear and how it actually physically works. So in this case, we're looking at lenses, and we're looking at two types of lenses. Two types of lenses. First, we're looking at a converging lens, and then a diverging lens. We're looking at a converging lens and a diverging lens. They're named appropriately. So a converging lens takes rays that are coming toward it and converge it or focus them. Have you ever, when you were a kid, used a magnifying glass to start a fire? True story. No. You can do it, obviously. How do you do it? What do?
You go out, and it has to be a sunny day, and you have to have a dry surface for the rest of everything. And you take the magnifying glass and you push it further away from the sun until you get the sun's rays focused into a tiny beam, and then whatever you come in starts smoking.
Yeah, it'll start smoking. If you do it with your hand, you could actually burn your hand too. Please don't do that. Don't do that stupid challenge I've seen online lately.
What is it?
The dumbest thing you'll ever do. You will literally have third-degree burns the rest of your life. You know what I'm talking about? This new thing with the ice? Salt and ice? Do not. Yeah, but now people are doing it to the point where they're literally trying to see who's tougher and getting third-degree skin burns. Your hair will never grow back. It will be white for the rest of your life. Your skin, like it'll be like not tan, not whatever color your skin is, but white. Like it will be literally, it'll look like you're albino at that point. Please don't do that. It's really dumb. Really, not like I don't understand who would be in this right mind to actually ever do that to themselves. Terrible.
Literally just ice and iodized salt.
It's exactly what it is. But regular table salt is iodized, or ionized or iodized.
So you just put table salt.
Don't even do it.
No, I'm not doing it.
You pretty much layer table salt and put ice on top. And it lowers the freezing temperature, salt, by default. That's what allows you to make like ice cream. It lowers the freezing temperature. So it gets super cool, and you get frostbite, and you'll get third-degree burns.
So it's so cold it burns.
Yeah, it's insane. Do not think about doing it. Now, if you take a magnifying glass, and if you were to move the magnifying glass, what you'll notice is that the light that comes from the sun gets focused in bigger or smaller circles, like a flashlight. Like the other day I was showing with the flashlight, when you move the flashlight away, the circle gets larger, right? Take a magnifying glass, you do the same thing, except the circle gets smaller, and it intensifies or amplifies the sun's rays on one little spot. And usually you do it on like dry leaves. You're going to start burning the dry leaves. So if you're ever, not that you would use this for camping because there's better ways to start like a campfire, but if you were really stranded and you had a magnifying glass, that would be one way to actually get a fire started. And that doesn't mean you have to have that. You could use your glasses to do it also. Any sort of lens will work. Now, for these lenses, we're going to talk about the two types. The first is converging. The second is diverging. Converging sounds like what it is. It converges the light rays. So the light rays go into the actual lens. So let's say these are the sun's rays. The sun's rays, appear to be approximately parallel because they're traveling such a far distance that by the time they get to us, they're really pretty much parallel to one another. Now what happens is it hits the actual lens. The lens bends it a little bit first. The ones in the middle don't bend as much. Then it exits the lens, which bends it even more. And right here is where it like focuses on. That's another word, or that's another time we're going to use that word focal point. If you recall from ellipses, remember planets, the sun was a focal point, and the empty space was the other focal point, and then this Earth traveled around it with 2 focal points. This is another time we're going to use that phrase focal point, okay, or focus. The focus is right here. That's the focus. Now, we're going to get to it in a second, but where the focus occurs tells you whether or not you can see well or not. If you can see far or near, if you're nearsighted or farsighted, if you have what's the other one? Astigmatism, it's a little bit different. That has to do with the shape of your eye. My 2 of my brothers have astigmatism, actually. And it's not always both eyes. So when you have astigmatism, you might have like one prescription for one eye and one prescription for the other. They're a little bit different. But here, what's happening is these light rays are getting focused. But if you need glasses, like me, I need glasses to see far. That means that the light rays that are focusing in my eye right now are focusing beyond the retina. And we're going to show this with a diagram in a minute on the next slide. Okay, but I want you to see how this lens could be used to correct that because it focuses the light rays a little bit earlier. If that's a converging lens, what do you think a diverging lens will do?
Not focus.
Yeah, they will spread out the rays if anything. Okay, they'll diverge, hence diverging lens. So these light rays instead look like this. So they're all coming in parallel. Separate scenarios, not the same scenario. They're all coming in parallel. And then based on the angle, refraction causes light to bend. Causes light to bend. Do you see how this is refraction, by the way? I didn't really point that out, but look here. If you can't tell, there's an angle right here. Here's the normal to the surface. The normal comes off the surface perpendicular always. Here's the normal at this part. Here's the normal over here. Here's the normal to the surface here. Those dashed lines are all normals. And our red light rays are coming in at an angle to the normal. So this is my incident angle. These are my theta i's, all these values here. That's the incident angle. So because it's coming in at an angle, refraction causes it to actually bend. Now, when it exits the lens, it bends even further. It bends even further. Okay, and this is not an obviously drawn to scale figure. I'm trying to really exaggerate the light rays actually bending through. If you want to see an exact example of this, in my notes, you can see I actually have a figure for this that I usually end up drawing to show you. But that's what it would look like. These are the actual rays coming through. Okay, so you can see these on my note. This is a converging lens. This is a diverging lens over here. Okay, the same things that you just saw above or in front of you, but seeing it with actual light rays. Now, the question was posed in the other class, what kind of lenses do we use to correct our eyes? Like, do we use diverging or converging? So let's approach that or attack that problem, that question. So if we look at this, we can see here that we have 2 scenarios. You could be farsighted or nearsighted. Let's start by the question, what does that mean? To be farsighted or nearsighted. Mike, what do you got?
Well, when you're nearsighted, you see better. You see things that are near you better.
Good.
And you can't really see very far.
Very good. So it's named accordingly. Nearsighted means you can see near. Farsighted, you can see far. You can't see either, you're neither of these two. You're actually a combination of both. And we'll talk about that with bifocals and progressive lenses and how they work. But the idea I want to start with is that when you're farsighted, besides the fact, God bless you, besides the fact that you can see far, the focal point, whoops, let me use the cursor, the focal point is too far behind the eye. It's focusing too far away. Farsighted. That's an easy way to remember this. When you're farsighted, here's the lens. Your eye has a lens in front of it. See this little thing? That's the lens right in front of the eye. The lens wants to focus this on the retina. Here's the retina right here. I'll put a little X. That's where the retina is, on the very back of your eye. Now, it wants to focus on that spot. But because the lens is maybe misshaped, or your eye is misshaped, your eye is a little bit long or short, as a result, what's going to happen is it's going to focus back here, too far away from the lens. Like this is where you want to focus, it focuses too far away. Well, if it's focusing too far away, and I want to make it focus a little bit sooner, I know that I need to put a converging lens so that this lens in the front right here gets these rays to start converging earlier. And then as a result, they hit the retina a little bit earlier. or they hit the focal point of their rays a little bit earlier, right on the actual retina. So that's a converging lens that's used to correct farsightedness. Most of you in the room, if you raised your hand earlier for corrective lenses, are nearsighted, right? I'm assuming you use your contacts to see the boards, drive, all that kind of stuff. Most people, as they get older, though, in life, become both. Or if they get corrective lenses for distance, they can no longer see up close. And you see old people, they use reading glasses. It's not to look like they're old or anything like that. It's to help them see. Their eyes actually physically change shape over life. Thankfully, I'm still, I guess, young enough that I can still read close, but even far, my eyes are pretty bad right now. I want to get the corrective eye surgery. I think I'm going to soon. And they create little slits in your eyes to help the rays to focus a little bit differently. The problem with it, though, is that if you get corrective eye surgery for distance, even when you get older, you're still going to need glasses for reading up close because it doesn't correct both of those things. Because that's like your eyes are degrading over time, really. So for nearsighted, which most of you are, the focal point is too close to the lens or too near. I don't know if that's really appropriate grammatically, but it's too close to the lens. So we want these rays to kind of separate a little bit and then come back together. So you put a diverging lens here. A diverging lens upon exiting causes the rays to diverge a little bit. Then the lens focuses them. So as a result, it doesn't focus too soon. It's a little bit further apart, so it focuses a little bit later, and it ends up right on the retina. Okay, so if you are farsighted, you use a converging lens. If you are nearsighted, you use a diverging lens. What are progressives and what are bifocals and those? What do they do? What's the whole purpose? Travis, you do something, yeah.
Bifocals is two sets of lenses that kind of split in the middle, and when you look down, you can read things up close.
Who was the inventor of bifocals? Do you know that one too? Ben Franklin. I only ask because it's like a common name. Ben Franklin, actually. And when you see pictures of Ben, good old Ben, we're on first name basis, me and him. When you see pictures of Ben Franklin, you can literally see a line in the middle of the glasses. And that's exactly right. There are two lenses that are fit together in one frame. They don't actually merge. They're not made of one material. Two separate lenses that are kind of locked in a frame. Now, that was kind of gotten rid of a long time ago. And the second step was not actually transitions yet. I'll show you, or not progressive, transitions are the sunglass ones. The second step was to do this. Take a look at the new set I put up here. These are if you've ever looked at a magnifying glass, there's a little extra magnifying glass in it. You have any idea what I'm talking about? Here, I'll show you a drawing. On a magnifying glass, there's your magnifying glass, right? If you look near the handle, you'll see another little lens right on the handle. On almost all magnifying glasses, they have the standard magnifying glass and then something else here that is like a super magnifier. It helps you to see really close up. Well, that's what's happening here. So the second set of lenses that were for people that needed corrective lenses for both far and near decided, well, you know what? If you're reading a book, you're looking down anyway, aren't you? That's why for bifocals, when you're reading a book, you would look out the bottom. But if I'm looking at you guys in the face and I had glasses on, I'd be looking out the top of the glasses, really. I'd be looking through the glasses around this location. But if I were doing this, ready? So I'm looking at you, and now I go like this. I look down to read. Where would I be looking? I'd be looking down, right? So these little areas here are little like mini lenses within the overall lens itself. Third and most recent are called progressive. That's not even worth me drawing them because there's nothing to draw. You can't even see it progressive. From a profile, though, anybody's parents have progressive lenses? Ask them tonight, please. I'm curious. If they do, take a picture. Take a picture from the side, the front, the back. I want to get a look at what they look like. Progressive lenses are made so that when you look out the top, you can see far. It helps correct for long distance. When you look at the bottom, you can see near. But it's not actually two different lenses at all. It's one lens that changes its shape throughout, hence progressive. It progressively alters its shape and its curvature so that you go from being able to correct seeing far to being able to correct seeing near. But the idea is that you look out the top or the bottom still. Okay, you direct your eye or your vision either at the top or the bottom. Progressive are not the same as transition lenses. Transition lenses are like Anybody have sunglasses? Or anybody have glasses that when they go outside turn into sunglasses? Jared, that's right. That's a great example. If you guys remember Jared Sinibaldi last year, Gerard. Jared had these glasses that they were ridiculous because he would come into school and it looked like he had sunglasses on. If you were in the sun, you haven't? Yeah, when you're in the sun for long enough, the lenses actually start to get like tinted. Those are transition lenses where the sun affects them and it makes them into like a sunglass lens instead of a regular lens. They still work for prescription, but they're also good for when you're out in the sun. These are progressive lenses where the actual magnification and the curvature, the diverging or converging nature changes throughout the actual lens itself. I don't know what the time is today, so I'm just going to keep going until it rings. Anything else for this that I want to talk about? No. Okay. Actually, I'm going to pause there. So, in this diagram, here's what we've got. We've got a stationary point that is a source of EM waves. In this case, think of the red line as a laser line. Okay, there's a laser pointer. I'm holding the laser pointer here at the bottom. The laser pointer goes perfectly vertical. It hits the surface of water and air and goes right out. Again, because it's not hitting the surface at an angle, therefore it goes right through. Remember, you need an angle of incidence to create an angle of refraction. Think back to Snell's law. Here was Snell's law. And Snell's law clearly shows us that, well, if your angle of incidence is just simply 0 or 90, it's not going to give you an angle of refraction. So you need an angle of incidence, whereas here, the angle of incidence is really just 0 degrees. Okay, remember, how do you measure the angle of incidence? You draw a normal. So for the second scenario, I'll draw a normal so you can see. And this would be the angle of incidence right here. Okay, I'll point to it on here so you can see later. Okay, that would be the angle of incidence right there for the second laser. Well, what's the normal? If you draw a normal on top of the first laser, the normal sits right on top of the laser itself. You really can't even see what I just drew. It's right here. Okay, the normal sits right on top of it. So what's the angle? The angle is just 0 degrees. So if I have an angle of 0 degrees, I put 0 degrees here. The sign of 0 turns out to be 0. So you're going to get 0 equals 0. So the refracted angle must be 0 also, proving that if you shine a laser or a light or an EM wave on a surface boundary, if it hits that boundary perpendicular, it's going to go right through. It's going to pass right through. Now, we take that laser. We start tilting the laser. As the laser is tilted, it creates a refracted angle at the top. And here's our refracted angle. Oops. Theta R. Here's our incident angle. I don't want that to be confusing. I can't erase it now. Here's our incident angle, theta I. So for the second scenario, I'm going to outline it so you can see. We're looking here. The laser hits the surface and it bends away from the normal. Again, it's bending away from the normal because it's moving into a faster material or faster moving material, air. Remember, air is the fastest moving material that lasers can travel or EM waves can travel through. So instead of continuing along this path, right, that's where it would continue, follow the line. It would continue in that direction. It's going to bend instead away from the normal. Now, if we continue to alter theta I, if I continue to take my laser pointer and instead of angling the laser pointer like this, like we just did, now I'm going to angle it a little bit further. Now I angle the laser pointer instead of being here and here. Now I'm on the third line. If I increase the angle of the laser pointer, well, let me draw my new normal. Now it's intersecting right here. There's my new normal for this one. The angle of incidence now, you'll notice, goes from being this value, doesn't matter what the number is, but to a larger value right here. Compare these angles, please. This angle right here that's drawn with the little curved line, compare that to this new angle right here, the blue line. It's obvious that this angle is getting larger and larger every time. So this is like a low angle, a medium angle, and then theta C here, we'll talk about that in a minute, is like your higher angle. Well, what's happening as this object or this EM wave travels, it bends even more. So instead of it being a theta R like this, now theta R, look how big it is. That's theta R now. It's a lot larger. This was theta R in that first case. Here's now my new refracted angle. So the refracted angle is getting bigger also as the incident angle continues to get bigger. Until what happens here, this is why I was talking about this earlier, until it bends so much being refracted that it actually bends back into the water, or back into whatever, in this case water, but whatever material you're in. So at one point in time, and you're going to see right here, it's going to travel and it's going to bend so much that instead of exiting the air, it bends right along the surface of the water. And this is what's a little bit difficult to demonstrate. The laser would literally ride on the surface of the water perfectly right there. Now, how many of you, this just came to my head, I didn't even think about this in the other class. Oh, it's weird. How many of you have been in an in-ground pool at night that has a light in the pool? Okay, so if you've ever looked at the pool from the outside, do you actually see light escaping the pool? The light is amplified in the pool. Doesn't the pool look like it's glowing like green or blue? That's what you're seeing here. I didn't even realize that. That's a perfect analogy or an example. The light is trying to escape the water into the air. But if you think about a pool, here's the shallow end, here's the deep end, here's the diving board coming into the pool. Okay, shallow end over here. Here's the water surface. Okay, the light bulb is usually right here. It's usually right near the water level. Do you notice that? I happen to have a pool when I grew up. That's one thing my dad loved swimming, so he got us a pool when we were kids. We put a pool in. So we had something like this. This light bulb is not at the bottom. It's not at the middle. It's actually at the top. The reason for that is because now when this light actually hits the water, it's hitting it at such a great angle. Right? Here, look, here's the normal. Here's the incident angle. Look how big that angle is. Theta I is so big that it's going to cause theta R, the refracted angle, to be very large. Well, when the refracted angle is very large, it means that it's really far away from the normal. Well, it's so far away that this light actually bounces back in. It's not being reflected, it's being refracted. Yet this is called total internal reflection, even though it is refraction. So again, the light ray gets bent so much that it bends away from the normal all the way back into the water because of refraction. So our goal in this section is to determine up here, this term, critical angle. And the critical angle is the minimum angle that causes total internal reflection. So in this case, you can see that here's theta C. I'll zoom in. Here's theta C right here. This is called the critical angle, this angle measurement right here, because at that angle measurement, instead of this continuing, right, which way should it continue? It should continue like that. That's where it should continue out of the water. It bends away from the normal so much that it's actually on the surface of the water. Anything greater than that angle will cause it to bend back into the water. So now draw your last normal right here, recognizing that this angle right here is the biggest of all the angles we've looked at now. Since this angle right here is greater than the critical angle, it causes this angle to be such a great value of refraction that it's actually greater than 90. Here's your refracted angle right here. That's the refracted angle right there. That value is definitely greater than 90. Like this angle here is 90 alone. Like that's 90 right to there to there. So this is going to be greater than 90. So if this angle exceeds the critical angle, it will bend back in. That's physically what's happening in a pool. This angle, theta I, is such a great value that it's gotten to be greater than the critical angle, what we call the critical angle. So it causes the angle of refraction, theta R, to be greater than 90 or bend back in. Okay, we're going to do a little bit of math now to explain this. So let's go into a bit of math here. What we can see first, okay, I write this so you guys can read it later, but when that refracted ray becomes parallel to the surface of the water, we say that theta I has become critical, meaning the angle that we're using to implement, to shine the laser at, has exceeded or at least equaled the critical angle. If it gets greater than that, we say it bends back in. Well, think back to this diagram right here. When the laser reached the surface and it caused it to bend along the surface, what's this angle right here? What's that value right here of this angle? How many degrees? 90 degrees. So when you hit the critical angle, here's the water surface again. Here's the normal. When theta I becomes such a great number that it reaches what we call the critical angle, the angle of refraction becomes 90 degrees. That's that angle right there. And the ray gets bent so much that the light is actually traveling along the surface. So what's happening here is theta r becomes 90 degrees. And this is where the math is going to come into play. So let's just jot down Snell's law. But instead of theta r, we're going to put 90 degrees. When theta r, when the refracted angle becomes so great that it's 90, it moves along the surface, the light ray. Well, the incident angle becomes what we call critical at that moment. It's the same thing. They're still the same thing, right? Incident and critical. Critical just means that the incident angle has become large enough for this to occur. So what we do is we replace the formula with theta c here instead. Okay, we call the incident angle, we say it has now become critical. It is critical in the sense that anything beyond that will continue to cause total internal reflection. So what that does for us actually is it allows us to solve this, because what's the sign of 90? It's 1. It's 1. So what we can do is we can solve for the critical angle and come up with a rule to give us the critical angle for any two materials. How do I get rid of sine? Good. And here's our new formula that we're going to use. This will give you the critical angle for any two materials if the ray travels from slow to fast. That's the big if statement at the end. For this to be true, you have to be traveling from a slower moving material to a faster moving material. From a slower to a faster. Before I go on, let me point something else out. If I go back up to this diagram at the top here, I'm going to zoom out so we can see everything still. If I go back up here, we said earlier this is water and this is air. What's the end value of air? What's the index of refraction for air? What was it? 1. Just simply 1. Well, that's the second medium, so that's actually NR. Right? We're starting in water, we're hitting a boundary and coming back into water. So we're never making it into that second material. What's the end value for water? For water. 1.33. That's in your table. If you don't have to memorize these guys, they're in your table. So those are the values. Well, it's always going to be the case that Ni is greater than Nr if we have total internal reflection. Because what did I tell you a little while ago? I said it's going to move from a slower material to a faster material. Well, slow materials have a higher end value. Fast materials have a lower end value. So it's always going to be the case that Ni is greater than Nr for this to be occurring. Again, Ni will always be greater than Nr if you have a chance at total internal reflection. If it's the other way around, and the light ray goes from the air into the water, it's not going to occur. I'm telling you now, it will never happen that way. Okay, it can never go from a fast-moving medium into a slow-moving medium and then bend back. It's not going to happen. And the reason for that, you can actually figure out. You'll see this in about, 2 units maybe in math. You're going to start trig soon in the 4th quarter. And you're going to see in your trig course that you cannot do the sine inverse of something that's greater than 1. So the denominator, Ni, will always be greater than the numerator, Nr. This expression, sine theta inverse, or sine inverse equals N of Nr over Ni equals theta c, cannot have a fraction in here that is greater than 1. And you can try in your calculator if you want to. Try to do sine inverse of like 1.1, 1.2, anything greater than 1. It will not work. You'll get an error. It has to be what's called the range of the sine function. The sine wave has a range to it. It goes from 1 to -1. Anything outside of that is not going to happen. So in this case, this will always be the situation where Ni, the denominator, is bigger than the numerator. If the denominator is bigger than the numerator, like in this case, We've got 1.33 and 1. Water is NR, that's what we're trying to get into. Air is NR, that's what we're trying to get into. Water is NI, that's what the laser starts in. If you evaluate this, you're going to get something in the 40s. I forget the number. Somebody in the other class did this. What do you end up getting as an angle here? 40 what? Quick, come on. Take calculators out when you get in, guys. When you get in, hand out. 40 what? $48.7. Angie, you agree?
Yeah.
Okay. I saw both you guys get on. Really good. 48.7. So that means that if the incident angle is greater than or equal to 48.7, it will bend back into the substance. It will not pass through the interface right here. So here's your angle. Take a look at the board over here. If this angle theta is greater than 48.7, greater than or equal to, really, 48.7, this ray will not escape the water. Even at a bent angle, it will not escape. It will bend back into the water. We call it critical because anything beyond that causes it to bend back into the material. That's why it's called a critical angle. I'm going to go on, then I'll show you another video in a second. So let's look at an example for this first one. Let's find the critical angle for light traveling from diamond into air. Okay, from diamond into air. And this is going to be a great explanation as to why diamonds have that tendency to like sparkle and trap light in a sense. So if I look at an actual cut of a diamond, diamonds are usually drawn like this, right? And so you see them drawn like the Superman shield. So the light rays enter the diamond. They refract or reflect off the inner surface of the diamond. There's metal, it bounces back. Now, as the light rays try to escape, so let's say the light ray comes in from here, hits the surface here, here's the normal. It wants to continue, but since it's going into a slower material, it bends away from the normal. Comes over here, hits here, bounces off, hits here, bounces off, hits here. What's happening here is this angle, or this diamond, the way it's cut, is able to trap the light, causing it to actually sparkle. That's why if you've ever, I don't know, I may have mentioned this to you guys. I went diamond digging once. Did I ever tell that story? Out west? Yeah, I did. It's no joke. So I'm not kidding at all. You can go diamond digging at like craters, because craters usually where asteroids or meteors have hit is a large diamond deposit. So I went with a friend of mine. Believe it or not, out west. We went for a bachelor party, just out for like a whole weekend. But one of the days we went diamond digging. I know, it's fine. We did. Yeah, true story. It's one of my best friends actually. And his wife is very like, she's all like about simple living. His wife is extremely rich. It's incredible. But she's very like down to earth and all about like simple living. And she didn't want like a big diamond for her engagement ring or anything like that at all. So we went diamond digging to find a diamond for her. I'm not kidding at all. It was an utter failure because if you actually do a little research, you'll find that in order to get a diamond that could actually be mounted, you have to get a huge diamond that could then be cut to be placed onto an actual ring. But if you find small diamonds, you can actually make like a pendant out of them. So we actually did find a couple small ones, one that was big enough that he actually made himself. He's like a machine expert. And he actually milled down the metal, he melted it together, he soldered, so he made a nice necklace for her with a diamond on it. It was really nice. But a diamond itself has to be cut because it needs to be cut to all these angles so that when it actually is embedded on the actual ring, it does actually sparkle. Even earrings. If you have diamond earrings, they're embedded into the actual metal stud or whatever you call it. Is the diamond the stud or is the metal the stud? I don't know, whatever. But the metal frame the diamond gets planted onto, well, it has to be cut at specific angles, so it has to be a big enough diamond. The angles are what cause it to sparkle. So if we could figure out what that angle is in this problem, we could see the exact number that diamond cutters actually use. So if we look at this, we see that it's traveling from diamond into air. So from diamond, that's where it's coming from, into air. Those are my values right off the bat. From diamond, meaning from that material, so that's the Ni value. Into air means to another material, that's the second N value. So we're going slower to faster. Very good. Slower to faster. Okay, it moves from a slower material to a faster material. Now, the question is, what's the critical angle? And you might say to yourself, well, we need another angle. We need either theta I or theta R. But we don't. We can assume theta R is 90 and go right to our formula for critical angle. And that's all we have to do is plug in those two numbers for n. Plug in nr, plug in ni. We can determine the critical angle for diamond. The sine inverse of 1 over 2.419. 24.4. Let's compare this now. It has no significance unless you can compare. 24.4. All right, seems like it's a low angle. Fine. Well, what was the angle for water we got in the previous slide? What was the angle for water? 48. Double that, right? So it turns out that for a diamond to trap light or trap an EM wave, the angle only has to be 24.4 or higher. That's a lot of possible values. 24.4 all the way up to 90 degrees. Any of those angles, if the light hits the diamond or hits the diamond on the way out, it will be trapped. So there's a very high probability that the light gets trapped inside of a diamond because any angle above this will cause it to get trapped. Whereas with water, it had to be any angle above 48. That's a much more limited range of answers. From 48 up to 90, that's only like 42 degrees of possibility. But from 24 up to 90, we've got like 66 degrees of possibility. So when you have a light ray exiting water, there's a much lower probability that it will actually get trapped than when it's exiting or trying to exit a diamond. So a diamond, that light ray comes in, goes into the diamond, and it actually traps and keeps bouncing, and that's what's causing it to actually sparkle. Yeah?
So if we don't have angles in the problem, should we just always assume
There's a good chance that if you don't have any angles provided, you're going to probably use this formula. But you should also recognize when it says find the critical angle, theta c, go right to that formula. Okay? Yeah, Snell's law is useful, but for Snell's law, you have to be given at least one of the angles to use it. Okay? Let's do the last one here. There's one more example, and then I'll talk about some theory. Oops. Oh, no, I'll go right into the theory. Okay, perfect. I thought I had one more math example. Let's see on that. So the theory is what I was talking about earlier, and I held up Maddie's iPad to show you this image. Well, this is called a light pipe. This is called a light pipe. It's pretty much simply just a piece of glass or plastic or some material that has a very, very high N value, like diamond. It has a higher N value, and therefore it is easily trapping light inside of it. Look at these angles. So let's zoom in so we can see what I'm talking about. Let's zoom in right here. Let's draw a normal. There's my normal. How do I know that's my normal? Because it's perpendicular to the boundary. Where's the boundary? The boundary that it's contacting is pretty much right here. There's the boundary right there. So I'm contacting this boundary. There's the normal. Look at the size of this angle right here. That's a very large angle of incidence. Right here. That is theta I. Theta I has to be greater than the critical angle for this to bounce back in. Well, this material is very much like diamond for its N value. So as a result, the angle here that becomes a critical angle might only need to be like 30 degrees. Anything more than 30 degrees, it'll get bounced back in. Look at theta I. That's definitely more than 30 degrees. It's almost, actually, if I look at it carefully, yeah, it's more than 45. If I were to draw 45 perfectly, 45 would probably be like that. That would be 45 right there. This is exceeding 45 by a little bit. So this theta I is greater than the critical angle for this material, whatever that material is. So instead of continuing out and bending a little bit, it bounces back in. Hits again, bounces back in. And the process continues throughout the entire light pipe. Okay, and that's literally what fiber optics are. Fiber optic cables, FiO stands for fiber optics. Fiber optic cables themselves are these light pipes, but they're carrying actual signals themselves, not just light. All right. The last thing for refraction, and this is not example total internal reflection here. It's called dispersion. And dispersion is just refraction, where, God bless you, diffraction where you have two different interfaces at two different angles. So it hits this, the white light hits this first, it's the prism here, hits the side of the prism and it starts to separate the light a little bit. It hits the other side, separates even more. So what do you see on the other side? You see all these different wavelengths, all these different frequencies. Different frequencies correspond to different colors. If you recall, Roy G. Biv.
That's the Pink Floyd one.
Yeah, that's exactly what the Pink Floyd album cover is, a prism with light being dispersed on it. That's exactly what it is. That's Dark Side of the Moon, is that what it is? Yeah. So if you think about Roy G. Biv, you have red over here and you have violet over here. Violet has the highest frequency. Red had the lowest frequency. And we talked about how infrared meant below red, ultraviolet meant above violet. Well, if you could break up a visible light into several different frequencies, you'll see all the different colors of the spectrum. All right, I'm gonna pause here. I'm gonna go on. I'm gonna show you a quick video, but that's it for this lesson. I put a little note there talking about how water droplets act like a prism. When you see, it's like after a rainstorm, you sometimes see a rainbow for a little while. It's because of the water droplets in the air. Okay, that's what's refracting the light.